Okay, so in the previous video, we went over the derivation of all of the equivalent circuit parameters for the common source. And so we derived these three equations and then this fourth one. Here are some kind of figures of merit, so to give you an idea of how big of a gain you should expect from a common source, what the input resistance should be, and what the output resistance is. And then in this particular sub-lecture, we're actually going to derive the common drain parameters, and the common gate are the next lecture. Okay, so let's get started. So again, remember, we're going to derive these equivalent circuit models for the common drain in this lecture. So here's our common drain circuit. And so just like we did before, we're going to first analyze our DC bias point. So to do that, we will open all capacitors and short all inductors. There's no inductors in the circuit, so we don't have to do anything there. So basically, we're going to open this circuit, open this circuit. So what's going to happen is that our DC model will consist of the same circuit with this removed, or the AC signal removed, and this part branch removed, or the RL removed. So this is what we have to actually analyze. This is the DC circuit. Now, if you notice, this DC bias circuit looks exactly like the circuit for the common source, except RD is equal to 0, and it also looks like the 4 resistor network that we analyzed in the first week of lectures. All right, so for this particular example, unlike in the common source, we're actually going to plug in some numbers. So here's the numbers that we're going to plug in. And so to analyze this circuit, we first find the source term. So remember that we're going to only need to look at this particular sub-circuit. And so we're going to separate that out. And so here's the circuit that we will get. And then we have that VD equals V plus because there's no RD. And in this particular case, we said that V plus was equal to 5 volts. So we're going to get that VD equals 5 volts. And then we're going to have that Vs equals V minus, which is negative 5 volts, plus RSS times ID. So we have that Vs equals 5 minus RSS ID. And then we have that Vg will actually be equal to, well, this is a voltage divider, so Vg will be equal to V plus minus R1 times V plus minus V minus divided by R1 plus R2. So remember, from here to here, the voltage drop is V plus minus V minus. And so that means that the current flowing through this, there's no current flow through here. So it means that the current flow through here is actually just V plus minus V minus divided by R1 plus R2. So this is the current. And the voltage here has to be the voltage here minus the voltage across this resistor, which is R1 times I. So V plus minus R1 times I, that gives us Vg. So VGS would just be subtracting out these two equations. Additionally, we have a final equation for ID, which is that ID equals VGS minus V threshold squared times K over 2. Okay, so here I actually wrote all that. So here I have VD's V plus, or 5 volts. Vs is negative 5 volts, or V minus, times RSS times ID. We don't know ID. Typically, since we know that what V plus and V minus is, in this case it's 5 minus 5, so this will be 10. And then they gave us R1 and R2. We will be able to calculate this in the next slide. And so Vg we can get a number for Vg. And then once we have Vg, we can solve the quadratic equation to determine ID. Okay, so here's actually the calculations. So I plugged in 5 volts for V plus, 1 kilo ohm for RSS. And so, and then I plugged in for R1 3 mega ohms, and for, sorry, 7 mega ohms, and R for R2 3 mega ohms, and that's going to give me that VG is equal to -2 volts. So that's going to give me that VG, which is -2 volts, minus VS, which is just this, is just equal to 3 minus 1K times ID. I can solve this equation for ID so that I get that ID is actually equal to 3 minus VGS divided by 1,000. And so here what I'm going to do is actually write ID in milliamps so that I don't have to actually divide by 1,000. So now I have that ID is equal to 3 minus VGS milliamps. So remember, 1 kilo ohm divided by I will just give me milli. Okay, so now that I have this equation, I just solved the quadratic equation, and that's going to give me that VGS has to be either -1 or 2. And VGS has to be positive because we assume saturation to get this equation. And if VGS is negative, we would be in cutoff. So once we know VGS, we can back substitute that into this equation to get ID. So in this particular case, 3 minus 1 minus 2 equals 1. So ID will be 1 milliamp. So you get ID equals 1 milliamp. We have that VDS equals 9 volts. So VDS is equal to 9, which is indeed greater than 2 minus 1, which is our V threshold. Okay, so we are indeed in saturation, so we're done. So okay, so once we solve this thing, we're going to get ID, which is 1 milliamp. So now we can actually determine what GM and RO are. In this particular case, we can just plug in 1 over 1,000 for RO and 1 milliamp for ID. And that's going to give us 1 mega ohm for RO. And then for GM, we have 2 times 2 times 1 milliamp. So we're going to get 2 milliamps per volt. So now we know GM. All right, so let's just for a little while, I'm just going to solve everything symbolically, and at the end we're actually going to start plugging in some numbers into our solution process. Okay, so now that we know GM and RO, we have to actually start doing our third step, which is solve for the small signal circuit. So in this particular circuit, the first thing is that we're going to inactivate all DC sources, meaning that this will become a ground, and this will become a ground, because remember, this is just a voltage source plus minus V plus and then a ground. So when we make V plus 0, that just becomes a ground. And then we're going to take all of our capacitors and turn them into shorts. So this becomes a short here, and this becomes a short. Notice how our drain is going to be grounded. So we're going to write our circuit model in a way that our drain sits at the bottom and our drain is grounded. And then the source terminal sits at the output side, and the gate terminal sits at the input side. And remember that there's always going to be a current source that points from the drain to the source. And then you're going to have a magnitude of GM VGS, and then this would be VGS here. And then we have our little RO between the drain and the source. So now we just simply connect things to it. So let's start from the gate side. So the gate is connected to R1, which is then connected to ground, R1. And notice that R2 is also connected to the gate and then ground, so this is in parallel to R2. And then here we're going to have R6 connected to the gate. which is then connected to our voltage source and ground, V sig. So our sig is disconnected to a voltage source and then ground. So we've already done all three branches of the gate. Now we did the drain already, which is just connected to ground. Now we need to go to the source. The source is connected to RSS and then ground. And then it's connected to RL and then ground. And then plus minus B out. So that's going to be our equivalent circuit. Notice that I kind of drew my pi model backwards. I put the drain in the bottom and the source at the top. Typically, to analyze these circuits, it's easier when you put the grounded terminal at the bottom of your circuit. You could put it at the top. It's not going to change anything. But do note that because I put the drain down now, this current source always will point from the drain to the source. And the RO always sits between the drain and the source, the little RO. Okay, now we're going to actually analyze this circuit to determine the gain. So here's the circuit that I drew in the previous slide. As you can see, this is just a cleaner circuit, and this is the circuit that we're actually going to use for our analysis. Okay, so now we're going to actually look at the gain. Before we do, let's figure out what this VGS is in terms of V out and V in. So V in is actually VGD, so V in is equal to VG minus VD. And V out is actually equal to VS minus VD. So if I combine these two equations or subtract them from one another, I'm going to get that V in minus V out equals VGD, VG minus VD minus VS plus VD, which is equal to VG minus VS. Okay, now that we know how to write, which is actually just equal to VGS, now that we know how to write that, now let's look at this nodal equation. So we're going to have that we're going to basically assume that going out is positive, so that we're going to have negative GM VGS plus 1 over RO plus 1 over RSS plus 1 over RL times V out equals 0. And we can replace for VGS V in minus V out. So V in minus V out. And so that's going to give us actually the following, which is that GM V in equals negative GM V in equals, or sorry, I'm going to move the GM V in to the other side so that it becomes positive, and then I'm going to have GM plus 1 over RO plus 1 over RSS plus 1 over RL times V out. Okay, so now I need to get V out over V in. So V out over V in will actually just be equal to, in this particular case, this is just 1 over the 3 in parallel. And so I'm just going to say that if I divide out by GM both sides, I'm going to have basically, so this will become a 1, and then GM will be common to all three of them. So this will become 1 plus 1 over GM times that. And so I'm going to have basically that, and this is just really RO in parallel to RSS in parallel to RL to the -1 power. And so I'm going to get that V out over V in is just equal to 1 over 1 plus 1 over GM RO in parallel to RSS in parallel to RL to the -1 power. I'm going to multiply the top and bottom by this in order to get rid of that factor in the denominator, and I'm just going to get, and I'm also going to multiply by GM, so I'm going to get GM RO in parallel to RSS in parallel to RL times GM in times RO in parallel to RSS in parallel to RL plus 1. And remember, if I want to know, so this would be AD. If I want to know AVI, I just have to set this to infinity, and that's just going to give me that AVI equals, so if I choose RL approaches infinity, that's just going to be GM RO in parallel to RSS divided by GM RO in parallel to RSS plus 1. Okay, so now we found the gain. In the next slide, I actually show it more cleanly. So let's go to the next slide. So this is the nodal equation that I wrote on the previous slide. And remember that we have a negative sign because it's coming in. And our convention is that coming out is positive. And then we basically solve for V out. And then once we have V out, then we end up with this equation here. And then once we have this equation here, we start doing some manipulation. So first we subtract out this from both sides, or add this to both sides, this times V out to both sides, so that we get this and this, and then we divide out, then we divide both sides to get our final equation. So that's what we got in the previous slide. All right, so now we're going to actually look at the common drain amplifier and the intrinsic properties. So just to recollect, what we want to do is come up with the equivalent RIS, RO, and AVI, and just remember that the R sig and V sig is what would be connected here. So R sig, V sig, and additionally on the other side, R load is what would be connected here, plus minus V out. This is Pn. So as a result, when we compute RIS and compute R out, we are going to treat this as an open and we are going to remove these two from our circuit. Okay, so here's kind of the equivalent circuit. So now I've opened the RL and I've removed R sig and V sig. And now we're going to use this to come up with AVI, RO, and RIS. Okay, so let's get started just like we did with the common source. As you can already see that this is a more involved circuit than the previous one. And then at the very end, we're actually going to plug in some numbers so that you can get an idea of how to actually come up with a numerical gain, which is what you're ultimately looking for. All right, let's continue with this. So next slide. Let's do this. So let's find the open gain. So like I said earlier, Vn is equal to VGD. Vout is equal to VSD. So that means that Vn minus Vout equals Vg minus Vd minus Vs plus Vd, which is just VGS. So the VTs cancel, and you're left with VGS. Okay, so that's going to help us because now when we look at this node here, we have this current coming in, so negative GM VGS, and then these two currents coming out, so we have plus 1 over RO plus 1 over RSS times Vout. That has to be equal to 0. And what that means is actually that Vout is equal to GM VGS times 1 over RO plus 1 over RSS to the negative 1. So all I did here is just move this term to the other side, and the negatives will cancel. And then I divided the whole equation by 1 over RO plus 1 over RSS. And that gave me this equation here. All right, so at this point, all I have to do is realize that this is just RO in parallel to RSS, and that this is actually just equal to Vin minus Vout. So now that I will have that we have that GM Vin minus Vout times RO in parallel to RSS. So now I'm going to move all the Vout terms to one side. So I'm going to get, what is this? Yeah. 1 plus GM times Rout in parallel to RSS times Vout equals GM times Rout in parallel to RSS times Vin. And then to get Vout over Vin, we just simply divide both sides by this and divide by this. So we're going to get that Vout over Vin equals GM little RO in parallel to RSS divided by 1 plus GM RO in parallel to RSS. That's it. That's our gain equal to AVI. And if you notice, in the previous expression that we derived, we had an RL in parallel to RO in parallel to RSS. So this is actually equivalent to plugging infinity for RO. So our open gain is always just the same as our normal game, except with an open circuit for RL or an infinite RL. Now we're going to actually derive our equation for capital RO and capital RIS. So here's that derivation again, typed up so that it looks nice and pretty. And now let's go ahead and do RO. So to do RO, remember, we have to set all other sources to 0. So in this particular case, we're going to set Vn to 0. And then we're going to do an Ix Dx test. So we're going to plug in not a current, a voltage source. Here, equal to 1. And remember that VGS is still equal to V in minus V out. And since we plugged in 1 for V out and we plugged in 0 for V in, we're going to get that VGS is equal to 1. Negative 1 because it's minus V out. So we have negative 1 here. And then now we can look at this nodal equation. And remember what we're actually after is Ix, because our O will be equal to 1 over Ix. Well, Ix will be equal to the sum of all the currents leaving the node. And so we have that Ix equals negative GM negative 1, so this is just VGS, plus 1 over RO plus 1 over RSS, which is just equal to GM plus 1 over RO plus 1 over RSS. And we can always write this in this funky way where it's GM is actually equal to 1 over GM. So that now what we're going to get is that RO is equal to 1 over Ix, which is equal to 1 over GM plus 1 over RO plus 1 over RSS, which is actually equal to the negative 1 power, 1 over GM in parallel to RO in parallel to RSS. So that's basically going to be our output resistance. And now we're going to look at the input resistance. But before we do, here I do it in a more clean fashion. And so here I plug in my Vx, which is equal to 1 volt typically, so that I get that VGS is equal to V in minus V out, which is Vx or 1 volt. And then now I have that Ix is equal to the sum of these 3 currents. And that's just equal to this, and then we're able to get that our output resistance is this. So note that this derivation is the same as the one before, except instead of plugging in 1 volt, I plugged in Vx, which means instead of RO being 1 over Ix, it's actually going to be Vx over Ix. Yeah, and finally, this will typically be in the order of hundreds, and these will typically be in the order of thousands, if not mega ohms. And so as a result, the one that's going to actually dominate is the transconductance. And so this resistance will typically be approximately 1 over GM. So this is just an extra fact. You don't actually have to know this. But do realize that this is kind of your limiting factor. And then your output resistance will typically be in the order of hundreds. Okay, so the next thing to find out is actually the input resistance. Again, to get your input resistance, we're going to short out V out. And then we're going to do an IXVX test, plus minus 1 volt. And now we need to figure out what IX is. And in this particular case, if I plug in 1 volt here, well, IX has to flow through here. So I'm going to get that IX equals 1 over R1 in parallel to R2, which tells me that RIS will be equal to 1 over IX, which is equal to R1 in parallel to R2. Note that I could have done the same derivation plugging in Vx. And then I have Vx over Ix equals Ri. So people typically don't use this 1 volt source, test source. They typically use Vx. And that's the way I was taught it. I've realized that in 2K1, people just plug in a 1 volt source. Turns out that it doesn't really matter what you plug in into this test source, as long as your input resistance is the ratio of the input voltage that you put as your test source divided by the input current. Okay, so now we got our final parameter. You didn't really need to do an IXVX test because in this particular case, you can just look at the input resistance as just R1 in parallel to R2. All right, now let's move on to our final slide. So here's actually the values we just derived. And here I actually want to show you that indeed the gain AV is actually equal to this equation here, which is just this voltage divider. So it's just AV divided by the sum of these two resistances times the resistance across the resistor. So that would be the voltage across that resistor. So I went through a lot of algebra to show you indeed that this gives you AV in the end. So this concludes actually our common drain. Now we're going to actually plug in some numbers and then. Okay, so now I will actually plug in the correct values for the common drain amplifier. And as we can see here, we have, so RSS is 1 kilo ohm. So we have 1 over 1,000. RO is 1 mega ohm, so 1 over 1,000,000. And then here we have that this is 0.02, which is the 1 over the transconductance, so that's just 2 milliamps per volt, so that's just 0.002 amps per volt. Okay, and so when we calculate that, well, this is going to give us 0.001, so we're going to get 0.003 roughly. That gives us 333 ohms. Note that if we had approximated as just as 1 over GM here, we would have gotten 500 ohms. So you see that you do get a pretty good approximation for the output resistance as just 1 over GM. And this is in the order of hundreds as we had expected. Okay, additionally, when we look at the input resistance, it's quite high. So we have the 7 and the 3 mega ohms in parallel. So we get 2.1 mega ohms. And then for AVI, we have to use this equation. So again, GM is 0.002, so 2 times 10 to the negative 3. RSS in parallel to RO, well, that's just equal to 1 over 1,000 plus 1 over 10 to the 6 to the negative 1, which is approximately equal to just 1,000. So we just get 2 in the numerator, and then in the denominator we have 1 plus 2, which is 3. So we get that our gain is about 3/2. So note that the gain is small. And in general, for a common drain amplifier, your gain will always be less than 1. Typically, people use common drain amplifiers mainly because it gave you a low output resistance, which is desirable, because the lower this resistance is, the more that will drop through this RL. So what you can do is actually connect a common source, which gives you a high gain, followed by a common drain, which makes you lose a little bit of your gain, but that gives you that low output resistance, which is ideal. So typical amplifier circuits involve connecting a lot of these amplifiers in series, and in your lab you'll actually have to build an operational amplifier which has, I think, 7 stages or 7 distinct different sub-amplifier parts. Okay, so that concludes our common drain circuit model, and the very last one, the common gate, is the next one.